Assalamu alaikum. Hello everyone. This is our 10th CS224 class, and I'm going to continue the class, the double precision, which was actually a topic from ninth class, but I couldn't do it because of the time. And basically today's goal is going to be about double precision, floating points and how to add them, also another floating points and how to multiply them. So let's get started. Okay, so as you can see here, this is our structure. We have a sign, an exponent, and a mantissa in double precision as well. The sign is 1 bit as a single precision. The exponent is 11 bits. Remember, the exponent in single precision is 8 bits. The exponent in double precision is 11 bits, right? And finally, the mantissa is going to be 52. If you sum 52 with 11 with 1, it's going to give you 64 bits, which is actually double the single precision. Remember, the single precision is 23 bits, and therefore double precision has its own name as a double. Then it makes sense now. Okay, remember when we said that the single precision in decimal is 127, which is actually 7f? Well, when we deal with double precision, we don't deal with we deal with another exponent, and that other exponent is 1023 in decimals, but it is 3ff in hexadecimal. That's everything. Let's get to one of the examples. Okay, so imagine I have minus 1024.5 as a decimal number, and they want to change it to hexa number. So how am I going to do this? This is pretty simple. Just ignore the negative, take the 1024 and do what we did like in the last class. Remember, we take the decimal number, we change it to hexadecimal number, and then we change this hexadecimal number to a binary number. So basically, 1024, we're going to divide it by 16, which is going to give us 64. And what is going to be the remainder? The remainder is 0, right? Remainder is 0. Remember, oh yes, since 0 is going to be our answer, I'm just going to write it in a different color. Then, what are we going to do? As I did in the last class, you're going to take this number, divide it again by 16. So it's 64 over 16, which I believe is going to give us 4, and the remainder is again 0, right? And then finally, you take this number and divide it by 16, which is going to give us, what is the answer? The answer is 0. And therefore, I'm going to write it in a different color. And this means the end of our division. We can't divide more than this, right? And then I'm gonna say remainder is so basically, since 4 is less than 16, the remainder is gonna be 4, right? And then what do? We take the number from down to up. So basically, we take it from 4, we take the remainder from down to up, from down to up. I guess I said it correctly, which is gonna be 400. So basically, 1024 is actually 400 in hexadecimal. Okay, now I just cleaned up the space so we can start as I said earlier, 1024 in decimal. Oh, that's a bad color, my bad. 1024 in decimal is actually 400 in hexadecimal. Now I want to know what is 0.5 in hexa number. So basically, you're just gonna write 0.5 and then you're gonna multiply it by 16. And what is the answer? 16 times half is 8.0. Oh, yes, let me also write this in a different color. When our decimals, like the result of multiplication, and our decimal is 0, this means end of multiplication, or like end of the operation, and we get that our 0.5 in decimal is actually 0.8 in hexadecimal. So basically, I'm just gonna change these question marks to 8. Okay, so as I said earlier, this is our decimal, right? And this is our hexa number. And what do we do next? Remember, next we change this hexa number. Okay, that is a bad arrow. We change our hexa number to a binary number. I'm gonna change it and come back. Okay, as you can see now, I changed the hexa number. This is a hex, but like it's a bad hex written, so forgive me. I changed the hex now to binary, and we get this whole number. Now, if you remember correctly, once we change our number from hexa to binary, we get what? We get the scientific notation. And since we are going to make this number smaller, our power is going to be positive. So basically, this is going to be 1 point. We're going to change this point to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So remember, we have 10 as our power, right? So now let me write everything after this dot. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, and then 0, 0, 0. And also I can add 0 here, but no need for it. Okay, so basically from this 1 till this 0, everything is copied, and now we get our number, but this is not everything. I need to multiply it by 2 power a, or 2 power 10, right? Because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this means yes, now I need to know what is the exponent of double precision. Remember, this is not single precision. So the exponent in double precision is 1023 in decimal, right? And in hexadecimal, it is 3FF in hexa, right? So there is either I'm gonna write 3FF plus A, and this is gonna be, so f is 15. If I add 1, it's gonna be 0, and we're gonna add another one here, and 1 plus f is gonna be 0, and another one here, so it's gonna be 4. And since I only added 1 from A to 3FF, it's gonna be 400, right? And then we're gonna change this A to 9 because A is 10, and I just added 1 to this. So they're literally the same thing. I didn't do anything except like making it easier to add. So it's like 409. And now this is our exponent number. This is our mantissa. Remember, this is our mantissa. And this is our sign. And remember, when psi is positive, it's gonna be, when sign is positive, the sign is gonna be 0. When sign is negative, it's gonna be 1, if I'm not mistaken. Let me check on this and come back. Yeah, so when it's negative, our 1 bit is gonna be 1. And now we're gonna change this 49201000000, and 9 is 1001. 1, 2, 4, 8, 8 plus 1 is 9. And remember, we said our exponent is 11 bits, right? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 bits, but our exponent says it is 11 bits. So what should we do? Remember, this is a crucial step, and you must always do it. Once you write your new exponent in binary, always delete the first, the most, what do more least the most bit from the left. Upper bit. I forgot what do we call this. So it's like MSB. I don't know. I forgot what was MSB standing for. Yeah, most significant bit. So remember, always delete the most significant bit, which is 0, and basically this is your new exponent: 10000001001. And now let me write our final result. So it's gonna be 0x. What is the sign? The sign is 1. Remember, sign is 1. Oh, and then I'm going to add, oh, this is not, sorry, we're gonna just write the binaries. So it's like 1, and then 100, 100, and 0000, and 1001. And now this is our sign with a diff. Okay, let me write it again so just people understand more. This is our sign, right? This is our exponent, and now it's time for our mantissa, which is this one. So I'm just going to add it also in multiples of 4 in order to change it easier later. So it's gonna be 0000, 0000. So this is like 1, 2, 3, 4, 1, 2, 3, 4. Wait, I'm becoming blind. 0000, 0000. Okay, and 001. Okay, 0 0 1 0, and then 0 0 0 0. Okay, the number went so, and this was here, and you're just gonna keep like writing the dots till you get like 64 bits, right? Let me just go a little bit down. And now I think, since this is the last one and all of them are zeros, we're just gonna fill up the next bits into zeros. So now let us do the normal thing that we used to do in single precision. So this is gonna be, this is 8 and this is 4. 8 plus 4 is 12, and 12 is actually C, right? A, B, C. B is 11, okay? And this is gonna be 0, so this is gonna be 0. This is gonna be 9, right? And 0, 0. This is 1, 2. So this is gonna be, wait, 1. Yeah, this is gonna be 2. And 0 0 0 0 0. 1 2 3 4 5 6 7 8. 1 2 3 4 5 6 7 8. 0x, and this is your final number, final solution as double precision. 0x c 0 9 0 0 2 0 0. So this is 1 2 3 4 5 6 7 8, and then another 8 zeros. 1 2 3 4 5 6 7 8. And I guess this is your final precision solution, double precision solution. Okay, how did I know that this is my final double precision solution? Remember, we said that single precision is only like 8 nibbles. Yes, 8 nibbles. So this is like, how many ones? 1 2 3 4 5 6 7 8. So this is 8. And now double precision, this is like only for single precision, SP. And for double precision, you add also the next part, which is 1 2 3 4 5 6 7 8. 8 nibbles. And this is in total, like all of this is going to be double precision. And yep, since it's double the single precision, then it's actually the correct answer. Okay, it's time to change this double precision machine code. It's time to change this machine code to double precision, and basically I'm just gonna break this machine code to binary numbers. Oh my god, it's always like this. Okay, now I can see it. So 4 is 0 1 0 0 space. 0 is multiple of 4 zeros, and 5 is 0 1 0 1, and F is 1 1 1 1, and 7 is 0 1 1 1, and then the rest are gonna be zeros, right? And 0 0 0. So these are like for, so, because like I don't have enough space. Okay, so do you remember the table? Let me bring the table and come. Okay, so the sign is 1 bit with a different color, of course. Let's take violet. So this is 0 and this is for the sign, and when it's 0, this means the number is actually positive. And then we said the exponent, which are made of 11 bits, and these are like 4, and these are 4 8 9 10 11, and these are going to be our exponent. So 1 0 0 is actually 4, and 0 0 0 is 0, and 0 1 0 is 1 is 5. So our exponent is 4 0 5, and then this is going to be our mantissa. We won't care till this number. We're just gonna care till the last one. You know, if the rest are zeros, then they're just zero expansion, and then we don't care about them. We just care till the last one. What if the number was like 0 1 0 1 0 1 0 1? Then you need to take all of these numbers till, even if the last bit of the 64 bits is 1, you're gonna take all of this as your mantissa, right? But because to get the right answer. So basically, remember, what do? We take this. This is our mantissa, and before we add it, we write with red color. How's this red? This is orange. Anyways, 1 point, and then you take all these numbers, which is with a different color. Let's say violet as well, since our exponent is in violet. 1 1 1 1 1 1 1 1 0 1 1 1, and this is our mantissa, right? And then it's 2 times 2 power something. What is this? What is this thing? We're gonna know when we just minus 3ff, um, which is the original mantissa. No, sorry, the original exponents. Okay. Uh, so 400 minus 3FF is actually 1. And then we're going to add 6. So it's going to just be 6. And we're going to take this and we put it here, right? Because 3FF, if you add 1 to it, it's going to be 400, right? And then add 5. Sorry, add 4. Add 5, yes. Add 5 is going to be 400. 5. So 1 plus 5 is 6. So this is our answer. Just a quirky math, whatever. So basically, our pointer is gonna move 6 points to the right. And let me delete this now, since you already. Oh yeah, this now. And let me point. Uh, okay. Okay. Red color. I'm gonna take this number and it's gonna be equal to. Let's go a little bit down. So the point is going to move 6 to the right. So 1, 2, 3, 4, 5, 6. So basically our number is going to be, let's do in dark green. 1, 1, 1, 1, 1, 0, 1.11. And remember, this is a binary number, right? But it is actually going to be written in hexa number, and then we're going to change this hexa number to decimal number. Don't do the same mistake I did in the last video, right? So this is going to be 1011. I think it's going to be, I don't know for now. This is going to be 7. So this is 7, right? because because like we have 0 here, so it's 0 1 1 1, and this is actually is 7, and then 1 1 0 1. So this is 1, this is 4, and this is 8. 4 plus 8 is 12, 12 plus 1 is 13, and 13 is equal to A, B, C, D. So this is 7D. And then point, don't remember, this is gonna be also C, right? Am I doing it right? I think I am. And now we're just gonna change this 7D to a decimal number. So 7D equal to, oh sorry, it is 7 times 16 power 1 plus D, which is actually 13. D is 13. 13 times 16 plus 0, multiplied 16 power 0. Let me do the math and come for it. You know what? I have the calculation next to me. So 7 times 16 is 112, plus 13 is 125, right? So basically this is going to be 125, and dot C is 12, so it's going to be 12 times 16 power negative 1, because so this is negative 1. The D is 0, right? The D in location 0, right? Because D is 13. 13 times 16 power 0. So C basically is going to be negative 1, right? So which is actually equal to 12 over 16 is going to be 3 over 4. And 3 over 4 is 0.75. I believe so, right? 3 over 4 is 75. Yeah, 0.75. So basically our final number is 125.75, and that's a floating point in decimal number. So that's everything about double precision. Okay, now our double precision is done. Let's see how can we add floating points, floating numbers. Actually, this should be floating numbers, not points. Whatever it is, I don't care anymore. Okay, so I have 9.999 in decimal number times 10 power 1 plus, and I want to add it to 1.610 times 10 power negative 1. So how we do this? First of all, you cannot add these numbers since they don't have the same base. As you can see here, let me change the thickness. As you can see here, I have a positive 1, I have a negative 1 here. So what should I be doing? I should change this whole number, so I get my power as 10 power 1, which means, so this is negative 1, right? Let me write it again. 1.610 times 10 power negative 1. Okay, if I move this dot from here to here, the negative 0 is gonna be 0. Negative 1 is gonna be 0 now, right? And uh, if I add 0 here and move my point to here, it's gonna be positive 1, right? Now we can add these numbers because they have the same base. Look, power 1 here, power 1 here. They have the same base. So basically I need to change this number to look like this number. And I actually did this right now. So let me just rewrite it again. So it's gonna be 0 point, change this number to this number. Okay, let me just have enough space. 0.016, and I can't add the 1. Why? Because as you can see, there are only 3 digits after the decimal, and the same here, there are only 3 digits. So this means we lost precision because this one is actually in one of, like, this one is already there in the original number, but we cannot have it because it's gonna be more space. It's gonna take more space, and this is not how scientific notation works. So basically, this is gonna be 0.016 times 10 power 1. Now we can add these numbers. So I'm just gonna take this number as a whole, gonna put it here, and then I'm just gonna write plus, and the answer is gonna be 6. Oops, my bad. 6 plus 9 is 15, so I have 5 here and 1 here with a different color, of course. So 1 plus 9 is 10, so I have 1 here and I have 0 plus 1 is gonna be 1, right? 9 plus 1 is 10, and another one 11, so I have 1 here. I mean, like, simple math, I don't need to explain it. So now I have 1 plus 9 is 10, 10 plus 0 is 10, so I have 0 here and I have 1 here, which is gonna be equal to 10.015 times 10 power 1. But remember, we want it to be in scientific notation, so this is gonna be changed to 1.001 times 10 power 2. As you can see, we lost the 5 here, and this means we lost precision, and that is actually how to add binary numbers. Floating numbers. Let me say the steps again. First of all, you equal them to the biggest power, to the biggest scientific notation, and in our case, the biggest power is 10 power 1, the smallest power is 10 power negative 1. So you gotta change this number, which is with 10 power negative 1, and you need to make it with the same base as this one, so it's gonna become 0.016 times 10 power 1. Now the bases are equal, 10 power 1, 10 power 1 in both numbers. Now you can add them, and then if your number is not in a scientific notation, you need to change it to a scientific notation one more time, and this is how you just add these numbers, floating numbers. Now we are done with floating numbers addition. Let's just get started with floating number multiplication, and we can end the video. Okay, now I have two floating numbers, 1.000 times 2 power negative 1. It's in scientific notation, and then I need to multiply it with 1.110 times 2 power negative 2. It's also has the same scientific, with 2 power negative 2. And both numbers are in scientific notation. So now we can multiply them, but before we multiply them, we need to add the powers. So basically, with a different color, and let's take the the orange, negative 1 plus negative 2, and this is gonna give me negative 3, and it's very obvious. I'm gonna use this later, but for now I need to have it. This is actually gonna be our final power. Like, it's gonna be like our final answer is gonna be the result of multiplication times 2 power negative 3. So for now, I don't need it. Now I need to take these numbers. Let's take Magneta. 1,0,0,0 times 1,1,1,0. As you can see, I just deleted the points, and yeah, you should also delete the decimals. Sorry, and you just need to multiply it as if it was a normal number. So I'm just gonna do the math to not waste your time and come back to you. So these are gonna be zero. Oh, okay, let me change the color. Magneta is gonna be 0,0,0,0, right? This is this is here going to be 0,0,0,0, and this is here gonna be 1,1,1,1. I put the 1. So this is the answer of multiplication. Oops, that's the wrong number. I just added a new multiplication and this is wrong. Okay, now it should be right. I hate this. I don't hate it, but I think I discovered better colors this time. I'm gonna have to choose blue. So it's gonna be 0,0,0,0,1,1,1. Your decimal is always gonna be in the end, which is the scientific notation, right? We want our number to be scientific notation, and then you're just gonna take this number. Okay, let's do it as if I didn't say the previous line. So this is gonna be your final solution of the multiplication, right? You're gonna write it one more time, one, and then we want it in scientific notation, so we're just gonna add the decimal, right? And then we keep writing the number one one, and at this point you can stop here. But if you want, you can also add the zeros if you want, and then it's gonna be, let's change it to red, times our base was 2, so it's gonna stay 2. And then what was the summation of our powers? Negative 2 plus negative 1 is gonna be negative 3. So this is gonna be actually 2 power negative 3. And this is how you multiply floating points. This is the final answer. Yep. Thank you so much for watching. Wait. Okay, this is how to multiply floating numbers. Thank you so much for watching. I hope you have learned and enjoyed. Take care and good luck in your midterms.